All right, here's our video today. Why the Earth spins or rotates, right? We could say spins or rotates. So I had a little rotate on the bottom here. Why is it rotates? Why does it rotate? Why the Earth rotates? That's a better way of saying it, right? Spins, rotates, because everything in the universe, well, we could just say our solar system for now, everything in our solar system, all the planets, the protoplanets, like the dwarf planets, asteroids and comets, everything is spinning. They're spinning, they're rotating, and even the sun rotates. And Earth is rotating. We'll have here's Earth's velocity. Earth is rotating at 1,000 miles per hour, spinning this way, counterclockwise. And our fastest planet, Jupiter. Jupiter is spinning faster. Jupiter's 11 times bigger than Earth. 11 times bigger than Earth. Yet, it spins 2.5 times, fix that too, faster. So our fastest planet is Jupiter. It's spinning, it's rotating. And our slowest planet, guess what our slowest planet is? Venus, slowest planet. A day on Venus is longer than its year. Imagine that. So why do they spin anyway? So let's get another page going here. All right, so like I said, the Earth is spinning and every planet is spinning counterclockwise. So let's write that up there. Let's change the color. Why don't we use green today? Counter, and we should increase the thickness too, right? There we go. Counterclockwise. Except two planets, Venus, which I mentioned before, the slowest planet, and Uranus. And try to pronounce it like that, Uranus. That's the way you pronounce it. So the Earth is going 1,000 miles per hour, or we can say 1,600 kilometers per hour. And it's spinning this way. And by the way, it is slowing down. We'll talk about that in a minute. So the question is why? Why is it spinning this way? Of course, when we're looking from where we are, let's say this is the ground, this is the Earth, it appears, let's use yellow for that, it appears like the sun is moving up into the sky. You know, it looks like the sun is actually revolving around Earth, which it's not. Many people did think that in the geocentric view of the universe before Galileo. So as it moves this way, the sun will appear to move up. And it moves more, the sun will appear higher in the sky because we're approaching it from west to east. So it's moving, the Earth is moving west to east. That's why you look to the east when the sun rises, and you look to the west when it sets. So again, the question in this video is, why is it spinning? Why is it rotating? Why is everything rotating in the solar system? And we have to actually go back to the origin of the solar system. So let's get a clean page for that. And let's stick with yellow. Why not? So we look at the birth of our, well, it doesn't want to do that. Let's go back. Let's go back. All right, let's try it over. We go back to our solar system's birth. Solar system. Birth. All right, so we're going back about 4.6 billion years ago. And during that time, a cloud of gas, not glass, a cloud of gas and dust collapsed. And where did this cloud of gas come from? It came from an exploding star, a supernova. It came, and we're talking about this cloud of gas and dust, it came from a star that exploded. And where did it explode from? We don't know. What was the star? We don't know. Was it where we are now in our space and time? Well, not in time, but Maybe it was the former owner of our solar system or the space within our solar system. But nevertheless, this was a supernova, a star that went supernova and exploded, and all this remnants of gas and dust was collapsing, and it collapsed due to gravity. So again, a cloud of dust, cloud of gas, collapsed due to gravity, and eventually a solar nebula would form. So this all this would equal a solar nebula. And let's look at a picture of that solar nebula. And if you need to write this down, I'll give you a few more seconds, or just rewind the tape. All right. And a solar nebula is just, a place where a star will form and eventually planets will form and anything else that's left over. So this cloud of gas and this gas over here, let's get our pen going. Let's keep the yellow one hot. So this gas started out as hydrogen, the lightest element in the universe, lighter than helium, and the most abundant element in the universe. And eventually, as this gas and this dust would kind of form together, they would clump together. The gas and the dust would clump together due to gravity. And you would get bigger and bigger and bigger material. And eventually, this hydrogen would fuse, would fuse into helium, second lightest element in the universe, and the one we use for our balloons. We don't use hydrogen balloons because they're flammable. They could explode. So if we had three helium atoms, four actually, four hydrogen atoms to make our helium. So H is the symbol for our hydrogen. And eventually, with all this gravity coming together, the gravity is lumping all this gas and dust together. You're getting higher and higher temperatures, and you need those temperatures and pressure so hydrogen could fuse into helium. And eventually, our little star would form. And then everything else would clump together too, all the planets and the gas giants. Jupiter would be the next planet formed. And as it formed, the nebula was spinning counterclockwise. So that's why the sun spins counterclockwise. And everything else that formed would have formed and then started their spin. And once you're spinning, you're not going to stop because of inertia. So let's talk about inertia next. And let's make sure we understand something again about this dust and gas. This dust and gas would clump together. There's enormous pressure with this gravity, enormous temperatures and heat. The hydrogen would form into helium. The sun would be born. The sun would spin as it started. The nebula was spinning right from the start. So the sun was born spinning. And then eventually other planets would lump together. The earth would gather material that was left over. And you would get this rocky planet. And then other planets would form also. So let's talk about inertia. So let's write it over here. Let's make sure our pen's working first, all right? Or else we go back to our planet spinning. The Earth wants to show itself. Well, let's just use this picture anyway. So with inertia, let's just change it. Let's change it to purple. Why not? With inertia, it's part of Newton's laws of motion. An object wants to stay in its state. An object wants to stay in its state. In other words, it wants if it is moving, it will stay moving. Unless a force stops it. That's inertia. And I have videos on inertia if you want to watch the inertia and a momentum video I have. And again, the vice versa. If an object is at rest, it wants to stay at rest unless a force moves it. So if you're sitting there in a field, you see a soccer ball, it's not going to move unless you kick it or unless the wind pushes it. So that's the force. And if you kick that soccer ball, it's going to stop eventually because of friction on Earth. But in space, there is no force to stop things. So once something starts spinning, it will stay spinning unless there's some force stopping it. And that may have been the case with Venus, why Venus has a different direction in its rotation. There may have been a planet or some kind of object that slammed into Venus, slowed it down considerably, and changed its direction. So in space, the reason why the planets are spinning, they're rotating, is because they started out that way in the solar system. They started spinning because of the gravity, the momentum. And once they were moving, they will stay moving unless a force is going to stop it. And there's no forces that will stop those planets. They could slow them down. I said in the beginning of the video that Earth is slowing down. Let's look at a chart. And this is why Earth is slowing down. Our friend the moon, La Luna, right? So the moon is tugging on Earth. We're tugging on the moon also. So this gravitational tug between Earth and the moon. So the moon is slowing us down. But not by much. Not anything that we can see or feel. And that tug that the moon is giving us is slowing us down by about 1.7 milliseconds per 100 years. So 100 years ago, the Earth was actually moving faster. And 100 years from now, it'll be slower, but nothing we would actually be able to notice. But let's look again at that chart. Here's a nice chart. You can see in the here and now. Get our pen ready there. Let's go back to red. Well, actually, we haven't used red today. So in our here and now, you can see our day is a little over 24 hours. Go back over 500 million years ago, it was about 21 hours. And if you go way back, all the way back, I mean, look at the time period. Close to maybe 12 hours was our day. So at one point, you can see just from the graph, there was a slope over here, right? And then we remained steady for a while. And then now we seem to be going up again. So again, the Earth is slowing down because of the moon. That's that force, but it's not enough to completely slow it down. All right, so again, that's our video today. Remember that the solar nebula, say that 3 times, the solar nebula clumped together, and all that gas by heat and temperature and pressure formed our sun, and then all the other planets would form by all those rocky bits and pieces and dust smashing into each other. And over time, you would have all these planets that we have. And the asteroid belt, by the way, is still remnants of that early solar system. And again, why is the Earth spinning? It's because of inertia. That's the key word. And it won't slow down unless there's a force that stops it. And there's a slight force of gravity from the moon. The moon is tugging on the Earth, slowing it down a little bit. All right, that's our video today.